Alright, so in this short tutorial, we want to talk about the factors that affect the resistance of a material or of a wire. Okay. Now we had a little bit of discussion in class in regard to why we want to know this, but to review, we want to understand how to take something and give it a specific resistance so that when we put in a circuit we get a specific current and therefore a power output. And so I liken this to a filament of a light bulb, but it can actually be to any wire because most loads, the resistance comes from some sort of wire, either curled or coiled or a straight wire. That is where the energy is deposited, usually in the form of heat, but it could be other things as well. Okay, so the first and most important factor that affects resistance is the material itself. Okay, we know that metals are very good conductors or have a low resistance compared to non-metals, which have a high resistance. So we need a way of quantifying the material, put a number to whether for copper or wood or anything else. This is something called resistivity. Okay, so it sounds a lot like resistance, but it's not. It's a close cousin to it, and it's given a symbol rho. It looks like a P, but it's really a Greek letter rho, and it's kind of like a lowercase r. So resistivity is a number that we assign to a material that gives us an idea of how good of a conductor it is, or how poor, or how low or high resistance it gives. So let's take copper. Copper we know is a metal. So what do we expect about its resistivity? We expect it to be fairly small. You might be surprised at how small it is. It's 1.2 times 10 to the negative 8th ohm meters. And this can be found in your reference tables. In fact, if you go to the electricity part of your reference tables, and we'll show this in class if you haven't done so already, you will see a whole about 6 or 7 metals, and you'll notice that all the resistivities are very, very low. Copper is one of the lowest, but it's not the lowest. Silver is the lowest. So that tells us that silver has the lowest resistance of any material for everything else being the same. But there are other things we can change so that we have 2 pieces of silver wire that have different resistances, even though they'll have the same resistivity. Nichrome is a wire that we find in a lot of appliances. It's wire we use for heating coils, okay, be it a toaster, a space heater, a hair dryer. Okay, so if you look at that, that's also in the reference tables. That's 150 times 10 to the negative 8th ohm meters. So it's still very low, and that's negative 8th, but it's much higher than copper. Okay, silicon, on the other hand, silicon is a very, very important material. It's a semiconductor, if you remember that from your periodic table. And silicon is the basis for all computer chips, all memory chips that we have in phones, computers, etc. Okay, it's one of the most important materials for our world today. It is a semiconductor, so it's not as good as a metal, but not as bad as a plastic. And its resistivity is around 1, give or take a few fat orders of magnitude. So what I want you to notice is 1 doesn't seem like a large resistivity, but compared to the metals, it's almost over 1 million times greater. So silicon is not nearly as good a conductor as copper and silicon. If we go to an insulator, then it jumps up to as high as 10 to the 10th ohm meters, depending on it. There's a wide range. But what I want you to notice is the resistivity from a conductor to an insulator is on the order of 1,000,000 trillion times difference. So that's why material is the most important factor for resistance. All right, the next factor that matters is the one that often creates the most confusion for students. All right, and it's the least obvious. All right, and that's temperature. Okay, for most materials, at least in this class, we're going to say higher temperatures leads to greater resistance. Okay, it's a very small effect. If we were to plot resistance versus temperature, we would see a very flat linear line. Okay, another way put, if I take a light bulb, the filament has a certain resistance when it's at room temperature. If I put it in a freezer, it gets colder, the resistance will actually go down. Not a whole lot, but it will be measurable. And if I heat it up, like by running a current through it, when that filament gets 1,000 degrees or so, its resistance goes up quite a bit. Okay, so a lot of materials follow this rule that large changes in temperature will give you small changes in resistance. Now you might ask, why would that be from a physical standpoint? Well, remember, temperature is a measure of atomic vibrations. So if we're at a higher temperature, the atoms are vibrating at a greater rate. Therefore, when electrons are trying to pass through the wire, pass through the atoms, there's going to be more it's going to be more difficult for the charges to get through because they are running into the vibrating atoms more often because they're vibrating greater and greater. We'll talk more about this in class because, like I said, it can be confusing. But again, higher the temperature, the greater the resistance. And a really neat application of this, I'll try to show you a demonstration class or a video in class, is superconductivity. You may have heard of superconductors before. They're relatively, even though it was discovered over a century ago, it's a relatively new technology where we can, for the right type of materials, under the right circumstances, we can get them cold enough that, I'm just trying to move this back, there we go, we can get something cold enough that material's resistance will literally drop to 0. And you get some really, really cool effects with that. We're talking so cold, we're talking a few, negative 200 degrees Celsius and such. So it's not easily achieved and only happens with certain materials. But I'll talk more about it in class. All right, so the B and C are the next big things that we want to talk about. We tried to do the Plato lab with this. That did not work out very well, but we want to discuss them anyway. So the next factor that matters is length. Okay, now, and without going into a lot of detail, longer wires simply lead to greater resistance. Okay, so if we were to plot resistance as a function of length, we would see it's a nice linear line. It's a fairly pronounced effect. What that means is doubling the length of a wire will give you twice the resistance. Having the length gives you half the resistance. It's as simple as that. So if I've got a piece of copper wire that's 1 meter and I've got an extension cord of the same wire, same thickness, and it's 10 meters long, then it's going to have 10 times resistance. And that can be significant if our wires get long enough. So this is a really important application for power lines, which have very, very, very long wires. We want to minimize resistance other ways for extension cords, speaker wires, etc. So I'll do some demonstrations with that, but there's not much more we have to say about that now. The other one is the thickness, and usually we measure thickness as an area, cross-sectional area. So if I'm looking at a wire on end, right, this is the area, okay? The area is going to be equal to, if this is the diameter right there, d, then our area is going to be pi times r squared, right, or pi d over 2 quantity squared. So thickness and area are related, they're not the same thing. But anyway, the greater the area, thickness leads to less resistance or lower resistance. And an easy way to think about that is think of a thick wire as like having more lanes in a highway. The more lanes you have in a highway, the wider the roads are, the easier it is for cars to get by. If you take 4 lanes and you narrow it down to 2 or 3 lanes, you're going to get a traffic jam. It's more resistance to things moving through. Okay, so let's answer a few conceptual questions here. All right, if you have a high-powered device, should the cord be thick or thin? All right, so what does a high-powered device do? High-powered device has a lot of current. And if we have a lot of current, then we have a low resistance. So if we want a low resistance, do we want it to be thick or thin? All right, we already chosen wire, so that's going to reduce the resistance quite a bit. But if we want to reduce it more, we definitely want it thick. So if you ever look at those devices like microwaves, power tools, things that draw a lot of current, up to 10 amps or so, their cords are usually pretty thick, because if they were really thin, the wires themselves would offer enough resistance that they might get really, really warm with all that current flowing through it. Would we want it long or short? Well, again, we want low resistance, so short wires give us that. And so notice those cords are not only thick, but they're short as well. The really long cords for appliances are generally ones that don't draw a lot of current or they're low power. So let's put it all together. So we have 4 factors that matter for the resistance. So we can sum it all up and say the resistance of any material is equal to the resistivity rho multiplied by the length divided by the area. And it's as simple as that. So actually, let me go back to the area one. let's, I didn't have any space for that, but let's make sure we're clear about the effects of resistance on area. Okay, so if area goes up, resistance goes down, so that goes by an inverse relationship. So you definitely want to know that. So coming back to this equation, we can look up resistivity, rho, based on the material. Length of the wire speaks for itself, and area can be found either as given, or again, area is pi r squared if you're given the diameter and you try to change the radius. And you might wonder, where's temperature in this? Okay, so temperature is a little bit complicated, but essentially the value of the resistivity is temperature dependent. So if you go to your reference tables, it'll say the resistivity at 20 degrees. Okay, so all our equations using resistivity are assumed to be at room temperature. What you have to know about temperature is conceptual. If the temperature goes up, understand that R goes up, and then current is going to go down, etc. Okay, so let's just finish up with a simple problem here. Okay, so what is the resistance of a piece of copper wire that's 30 centimeters long and has an area of 2 times 10 to the negative 7th meters squared? Okay, now that might seem like a really, really tiny area, but that's really just based on a wire that is about as thick as a millimeter or so. All right, so I'm looking for resistance. I'm not going to use Ohm's law because I don't know voltage and current, but I can use this equation, rho L over A. I look up copper in my reference tables, and it's actually on the top of our sheet here, 1.72 times 10 to the negative 8 ohm meters. It's a really poor ohm meter. Our length, 0.3 meters, divided by our area, 2 times 10 to the negative 7th meters squared. So if you look at our units, meters times meters cancels out the meters squared, and I'm left with ohms, which is, of course, what we want. So when we punch it out in our calculator, okay, I believe, I have this already, we get a very small resistance, 0.026 ohms, which we'd expect from copper that is not too long and a nominal thickness. Okay, so that should be consistent with what we expect. If I were to do the same thing with a piece of wood, the length and the area would stay the same, but this would go up to like 10 to the 8th. So we would have a huge resistance like we'd expect. Now, what if we were to look at nichrome instead? Well, what's the difference between these two situations is the resistivity. So I can say the resistance of nichrome compared to the resistance of copper is nothing more than a ratio of their resistivities, because we're comparing the same lengths in the same areas. So if I look up nichrome, its resistivity, or look in the middle of the sheet here, I see it's 150 times 10 to the negative 8 ohm meters. Copper, again, is 1.72 times 10 to the negative 8th resistivity. And if I divide those two, the ohm meters cancels out, and I get 87 times the resistance. Okay, so nichrome is a lot more resistive than copper, but it still has a low resistance. All right, if I take 87 times 0.026, I still get a fairly small resistance compared to other materials. All right, so that sums up the idea of the factors affect resistance. We'll do more practice in class and show some demonstration.